Hello everyone, welcome to this coding challenge video. Today we'll be solving an interesting problem that involves calculating the probability that a knight remains on a chessboard after making a given number of moves. My name is Sarvesh and I'm excited to walk you through this problem step by step. Let us now look into the problem statement. In this problem statement, you are given a chessboard of size n cross n and a knight piece starting at a specific position on the board. The knight moves according to its usual rules in chess, where it moves in an L shape, either 2 squares in one direction and 1 square in perpendicular direction, or 1 square in one direction and 2 squares perpendicular. Let us now assume that the knight's position is at 0, 0. At each step, the knight has 8 possible moves as shown in the figure here. The first possible position is 1, 2, that is 1 square down, 2 squares right. 2, 1 it is 2 squares down and 1 squares right. 2, minus 1 is 2 square down and 1 square left. 1, minus 2 is 1 square down and 2 square left. Minus 1, minus 2 is 1 square up and 2 squares left. Minus 2, minus 1 is 2 squares up and 1 square left. Minus 2, 1, 2 squares up and 1 square right. Whereas minus 1, 2 is 1 square up and 2 squares right. These are the possible movement for one knight in one position. So now let us understand this logic more easily by considering a 3x3 chessboard. And in this chessboard, the knight is now placed at the leftmost corner, which is considered to be the 0, 0 index. Let us keep the k is equal to 2. So for k is equal to 1, now the knight has two probabilities to go to the next position. Either to the upper arrow side or to the lower arrow side. It has two options. For each of these options, it has 0.125 probabilities. From each of these positions, now the knight has two options. So on total, the knight has now 4 options. For each position, it has 0.0156 probabilities. To find the sum of probability, it is given by 0.03125 plus 0.015625 plus 0.015626, that is equal to 0.0625, which is nothing but the probability that a knight can move after 2 moves. So to solve this problem, we are using dynamic programming. Before going to the code, let us understand the algorithm clearly. So the first step of the algorithm is anytime the knight has 8 choices to choose, inside as well as outside. The second step is moving the knight and check if it is inside. The third step is if inside, probability of taking new position is 1 by 8 of current probability. Repeat the point 2 and 3 until k number of steps are taken. For example, if we have k is equal to 2, then we have to repeat the second and third step for 2 times. If it is 3, then for 3 times. For how many number of times the k is asked, we will be doing the second and third steps again and again. So this is the algorithm that we are going to follow to solve this problem. Now let us look into the code thoroughly. We start by defining a list called moves that contains the 8 possible moves a knight can make on a chessboard. Each move is represented as a tuple with the change in row and column coordinates. The very next step that we do is initializing the probability array. So this is the step for initializing the array. Here we create a 3D list called DP, which is used to store the probabilities of the knight being at each position on the board after each move. The dimensions are k plus 1. This k plus 1 is used to denote the number of moves plus 1 for the base case of 0 moves. N, the number of rows and columns on the chessboard. Initially, all the probabilities are set to 0. Now the very next step that we do here is setting the starting position probability. Here we set the probability of the knight being at the starting position x, y after 0 moves to 1. This is the base case for our dynamic programming approach. The next step is for the loops. The outermost loop is for iterating over the steps. The purpose of this loop is to iterate each move from 1 to k. We start step from 1 because we already initialized the probabilities for step is equal to 0, that is the starting position. The loop continues until step is equal to k, which represents the total number of moves we want to consider. This loop helps us build the probability step by step, where each iteration corresponds to one additional move made by the knight. The middle loop. This loop is for iterating over rows. This loop iterates over each row of the chessboard. The I represents the current row's index. This loop runs from 0 to n-1, covering all the rows on an n cross n chessboard. This allows us to examine every possible position on the board for each step. The inner loop is for iterating over columns. This loop iterates over each column of the chessboard for a specific row. J represents the current column index. Similar to the previous loop, this runs from 0 to n-1, covering all columns in the current row. By combining this with the previous loop, we can access every square on the chessboard, that is every position I, j coordinates on the particular board. The innermost loop is for iterating over knight moves. This loop iterates over all possible knight moves from the current position. Like said before, it runs for 8 moves. Each move is a tuple that represents a potential change in position. For example, 1, 2 means moving down 1 row and 2 columns. The knight can't make any of these moves from its current position, so we need to check each one. So the very next step that we are going to do is calculating the new position. The new position is calculated by the statement ni, nj is equal to I plus move of 0 plus j plus move of 1. To calculate the new position after applying a knight's move, here we add the changes defined and move to the current indices I, j. Ni and nj represent the new row and column indices after making a knight's move. Now validating the new position is our next step. To check if the new position is within the bounds of the chessboard, we ensure that both ni and nj are valid indices, that is, they must be between 0 and n-1. If this condition is true, it means that the knight can legally occupy this new position on the board. After checking for the new position, whether it's inside the boundary, we now update the probability in our 3D table. In order to update the probability of the 3D table, we do this step. We take the probability of being at I, j after step -1 moves and distribute it evenly among all possible knight moves, hence dividing by 8. This reflects that if there are multiple ways to reach a certain square, each way contributes equally to its probability. Let's see how this works step by step when we call for k is equal to 1. When we call knight probability of 8, 1, 0, 0, the first step it does is it initializes our DP array as follows. For the first iteration, that is step is equal to 1, for I is equal to 0 and j is equal to 0, move 1, 2 leads to ni is equal to 1 and nj is equal to 2. So it gets validated and it updates the DP array as 0.125. And then for move 2, 1, similarly checks if it is validated or not validated, and it is validated, so it updates as 0.125. For move 2, -1, 1, -2, -1, -2, -2, -1, -2, -1 and -1, 2, it becomes invalid, so all these becomes skipped. After processing all positions for step is equal to 1, our DP array looks like this. So finally, we are supposed to calculate the total probability. So we use the function sum of dp of k. So the final result is stored in the variable total probability. So the final value is then printed by rounding off by using string formatting. That is 0.2500. Let's now calculate the time complexity of this code. So k represents the number of moves, n is the size of the chessboard, and 8 is the number of possible knight moves. So first step is iterating over the number of moves. So this contributes a factor of k to the time complexity. Next step is iterating over the rows and columns of the chessboard. This contributes n cross n. So n square factor to the time complexity. Next is iterating over the possible knight moves, that is 8. This contributes a factor of 8 to the time complexity. Calculating the new position and checking if it's within the bounds. They have a constant time complexity of order of 1 and do not contribute anything to the overall time complexity. Updating the probability in the DP array. Even this contributes constant time complexity and does not contribute to overall time complexity. Calculating the total probability. However, since it is performed after the main loops, it does not contribute to the overall time complexity. Combining all the factors, the overall time complexity of the knight probability function is order of k into n square into 8. This means the number of k moves at the size of the chessboard, n, increases. The time taken to execute the function will increase linearly. It's important to note that space complexity of the function order of k into n square due to the DP array, which stores probabilities for each step and each position on the chessboard.